Okay, in this video I'm going to introduce the idea of area under the curve with what's called a Riemann sum. Now we're still in section 5.1 and 5.2. I've combined those sections. I've already talked about sigma notation, and so we're going to look at area and the definite integral in the next couple of videos here. Now suppose that I wanted to find the area underneath the curve y equal x squared between 0 and 1. Well, that shaded region there is not like a common geometrical shape, so it's not like just go to a area of a triangle or area of a trapezoid or something like that. Okay, I'm going to use rectangles to estimate the area under this curve from 0 to 1, and I'm going to let the rectangles each have a length, each have a width of 1/4. Okay, I'm also going to draw the rectangles so that the right endpoints touch the curve. Okay, and so I've got that set up here. I'm using a width of 1/4 in creating 4 rectangles, and the right endpoint of each rectangle is going to touch the parabola there. Now I know area of a rectangle, that's very simple, right? It's just length times width. So if I were to calculate the areas of these 4 rectangles and then add them together, I can have an idea of what the area of that shaded region would look like. Now, I wouldn't know exactly the number, right? It would be an overestimate, since I've got all 4 of these rectangles have part of them hanging above the curve. I would get a number more than it should be, but at least it would be an idea of what that shaded area would look like. Okay. Area of a rectangle is length times width. Now the length of each one of these rectangles would be 1/4. The height is going to change depending on which rectangle you're talking about. But to get the height, you would be the y value for the particular x value. Okay, so like if x is 3/4, then the height of that rectangle would be just simply where I plug in 3/4 into the square function. And I would just be plugging in these numbers that produce the right endpoints into the square function in order to get the heights of these 4 rectangles. Okay, now the area of the 4 rectangles I'm going to call capital R sub 4. Okay, this is notation that you'll see in the book. R means right endpoints, 4 means 4 rectangles. And I'm going to be adding up the areas of these 4 rectangles here. Okay, using summation notation, you'll be seeing that in the book, and the area of each rectangle is length times width. Now the length is 1/4, right? And they're all the lengths are all the same here for each one of these. The height is just where I plug in increments of 1/4 into the function. Okay, the index is I, so f of 1/4 times I would get me the height of the ith rectangle. Like if I is 1, f of 1/4 would get me the height of the first rectangle. If I is 2, f of 1/2 would get me the height of the next one. If I is 3, f of 3/4 would get me the height of the next one. If I is 4, my upper bound there, 4/4 is 1, and so f of 1 would get me the height of the last rectangle. Okay, and of course f of x is x squared, right? So f of 1/4 I would be 1/4 I squared. 1/4 times 1/16 is 1/64. Constants can come out of sums, and I'll still have the I squared left in the sum. And okay, I'm adding up some squared terms there. I could use my special summation formula that we talked about earlier, this one here. N would be 4. So I'm going to have n times n plus 1 times 2n plus 1 over 6. N is 4. You're going to have 4 times 4 plus 1 times 2 times 4 plus 1 all over 6. When you simplify that, you should be getting 30/64, which would reduce to 15/32. Okay, now that would be an overestimate, right? Because all 4 of these rectangles have a part that is above the curve. Well, that's okay. It's still an estimate. And I could also know that the area of the shaded region would be a little bit less than 15 over 32. Okay, now let me redraw the curve again, y equal x squared. And I'm going to let each rectangle have a width of 1/4, just as before. But this time I'm going to let the left endpoints touch the curve. Okay, so I've drawn 4 rectangles. The left endpoint of each rectangle is going to be touching the curve. And I'll go ahead and calculate the areas of these 4 rectangles and add them together. Now in this problem, I'm going to be underestimating the area since all 4 of these rectangles are below the curve, right? Now the heights of the rectangles are listed here. You're just going to be plugging in the value that produced that left endpoint. So I plug in 0, plug in 1/4, plug in 1/2, plug in 3/4 to get me these endpoints here. And that would also tell me the height of the rectangle. Okay. Length times width. Now L sub 4 means that you're using left endpoints and you've got 4 rectangles. Again, this is notation that you'll see in the book. And so, okay, the area of the first rectangle, 1/4 times 0 is 0. The area of the next rectangle would be 1/4 times 1/4 squared. The area of the next one would be 1/4 times 1/2 squared. And the area of the last one would be 1/4 times 3/4 squared. If you add all this together, I was getting 7 over 32 as the total area, which is an underestimate. Okay. Now I was talking about sigma notation earlier. You could use that anytime you want if you're adding up a bunch of things. And so here's what that would look like using sigma notation. So the sum is I equals 0 to 3 of 1/4 times f of 1/4 I. I could just verify that. Like if I is 0, f of 0 would get me the height of the first rectangle. If I is 1, f of 1/4 gets me the height of the next one. If I is 2, f of 1/2 gets me the height of the next one, and then we're ending at 3, so f of 3/4 gives me the height of the last rectangle there. Now you can only use your summation formulas if you're starting at 1. Take note of that, all right? Not if you're starting at 0 or any other number. So in setting this up, I consider that I wouldn't be able to just use my formulas then that I showed you. Now I could certainly rewrite this sum, so I'm starting at I equal 1 and be able to apply that. And that would be ideal if I had many rectangles that I'm adding. I'd want to consider that. Okay, so the area of the shaded region I know has to be bigger than 7 over 32, but smaller than 15 over 32. I'll call the area of the shaded region capital A. Now, maybe a better approximation out of these 2 that I showed you would be, instead of using left endpoints or right endpoints, what if we had the midpoint of each rectangle touch the parabola? Okay, and again, I'll draw 4 rectangles here and draw them in such a way so that the midpoint of each rectangle touches the parabola. Well, the area of each rectangle would be length times width. The width is 1/4, and the height would be, whatever the y value is here from the midpoint that was selected. Okay, f of x and y are the same thing, so I would just plug in the x value to get me that height. The first midpoint is 1/8, the next one would be 3/8, next one would be 5/8, next one would be 7/8. Okay, and I can square those individually to get the heights. Since the width would be the same in each one of these, in computing the area, I've factored out 1/4 from the whole thing. I guess just like I did over here, factor out 1/4, you factor out a 1/4 on this part if you want. If we add up the heights then, okay, I was getting 21 over 64 when you simplify that. Now 21 over 64 would be between these 2 numbers. Okay, and that would, in this situation, that would be like probably my best approximation method. Okay, now in general, L sub n is going to represent the lower sum where there's n rectangles, and R sub n is going to represent the upper sum where there's n rectangles, and A is going to represent the area underneath the curve that you're wanting to calculate. Okay, here I was using a parabola. What if we're using any ordinary curve? Okay, A is going to be the area. Now, this inequality would be true for an increasing function. Okay, in other words, an upper sum means that you've overestimated the actual area, since parts of the rectangle would be above the curve. Okay, a lower sum would be an underestimate, since parts of the rectangle would be below the curve. Now, if the curve is decreasing, then that wouldn't be true, right? If the right endpoints on a decreasing curve would produce rectangles that are below the curve then, okay? Now, the more rectangles that you build, the better. You know, in that last example, I was only using 4 rectangles. Well, what if I were to use 50 rectangles? Okay, well, I would have a really good idea of what the area of the shaded region would look like, because there would be less wasted space, right? So the more, in general, the more rectangles that you build, the better. Now, ultimately, as n approaches infinity, n is the number of rectangles, the limit as n approaches infinity of L sub n would be A, and the limit as n approaches infinity of R sub n would also be A. In other words, as n is approaching infinity, the width of the rectangles are getting smaller and smaller, okay, and so the area becomes more exact, okay. Here's just kind of a picture redrawn with y equal x squared, and I've got n rectangles, let's say. You can see there's less wasted space there. Okay, and ultimately the rectangles would approach the curve itself, giving you the area under the curve that you'd like to find. All right, here's some more notation. Let's let delta x be equal to b minus a over n be the width of each rectangle for an ordinary curve f of x. Okay, A is your start point, B is your end point. N is the number of rectangles that you desire to have. X sub 0 is always going to be the same value as your start point. Okay. X sub 1, now if you're using right endpoints, let's say, your first right endpoint would occur at 1 increment of the width away from your start point. The width is delta x. X sub 2 would be where the next right endpoint would occur, and that would be at 2 increments of the width away from your start point. X sub 3, the next right endpoint would be at 3 increments of the width away from your start point, etc. B is where you're ending, and x sub n, we'll let that be equal to b. Now, if you're using right endpoints, you are at n increments of the width away from your start point. Okay? A plus n times delta x would get you that last right endpoint there. In the problems that you'll see we'll do later, I've arranged those calculations because we're gonna need to know, kind of see a pattern in order to set up our summation here in the calculation. Now, if f happens to be positive, then the sum of the areas of the rectangles is called a Riemann sum. Okay, that's a term in the book, a Riemann sum then is just where you've got n approximating rectangles that you're adding together to find the area under the curve. Now, if that number is a positive, because area can't be negative, then we call that a Riemann sum. Okay. We'll take a look at some examples of calculating upper and lower sums, and I'll talk more about a Riemann sum and the idea of area here in the next couple of videos.